LIGO Sound Doctrine continuing our explanation of the polyphonic and monophonic various kinds of synthesizers that use storage. Here we're basically talking about. Let's start out by talking about a little circuit here. I've got a little triangle drawn here. How well you can see it, but there are two types of devices that normally use that. One's called the operational amplifier, one's called a comparator. The op-amp, or operational amplifier, is named thusly because it can perform mathematical operations in analog voltages. For instance, you have a 2-volt signal, and you can have an adder which adds a 3-volt signal to it, and the output is 5 volts, hopefully, approximately. The problem is, the downside with analog world is it's all subject to the complexity of nature, and imperfections happen, but you build devices as precisely as you can, or sometimes sloppier, to have other complex natural anomalies enter into the picture. And in musical circuits, this can be a very interesting thing. For instance, some old effects pedals, people prefer using old, slow, weird op-amps that aren't anywhere near up to today's standards, but they just sound better sonically in particular pedals. So people still use those. Anyway, the operational amplifier and the comparator is very simple. It compares two voltages, and it has a plus and a minus input, which are called on op-amps and comparators inverting and non-inverting. The non-inverting is the plus sign, the minus is the inverting, and the output comes out there, and you usually have a voltage rail plus and minus here, which my instructor failed to tell me that at first, and I was like, how does this thing work? It doesn't make any, can we just get the power to do this thing it's doing? But yeah, they get fed a voltage supply that has a lot of current capacity, and meanwhile these are very high impedance inputs, and on an ideal operational amplifier those have essentially infinite resistance, and there are some that come very close to that using MOSFET technology. And so these particular devices that are used in most of the synthesizers you see are either junction FETs, which are on the order of nanoamps of input there, 10 to the minus 9th amps, in other words. MOSFETs can do 10 to the minus 12th, but they're not used very often. They're more sensitive. Of course, if you pull them out, you can zap them and destroy them by storing too much charge on one of those and burning out the insulative gate that's very thin there. Now, many of them are bipolar, though they use conventional transistor inputs, which have more like microamps or so impedances that will draw that much current at normal voltages that you're using, 5 to 10 volt, whatever, input. Now, one of the common ways to hook one of these things up, since you've got basically a transistor pair in here that pits these signals against each other, and if the plus or the non-inverting side is a higher voltage than the inverting side, the output will go high, and it will do so. Most of these have a gain of like 10,000. If they're just comparing the voltages here, it will very quickly go to rail, even if it's a tiny amount of voltage difference between these two inputs. But that's a good thing for the purposes we're going to use them for. Now, the negative side here, the inverting side, if it's higher, then the voltage will tend to go low on the output. Now, you can do various things with them. You can hook up a line from the inverting side to the output, and now we've created a voltage follower, because anything this voltage does, this output has to do, or try to do, and it will do so within the current delivery capability. Some op-amps deliver to 600 ohm, some 1000 ohm loads without distorting, and some more. But the basic thing that happens here, if you have, when you initially turn this circuit on, you've got 0 volts here, okay? And then as soon as you turn it on, let's say you already had 1 volt on a capacitor here. Then when you turn that amplifier on and it begins responding, it's going to go from 0 volts very quickly up, because this value is higher than the 0 volts that's setting on this line. And so now we will have a signal that shoots right up to 1 volt, and then obviously if it goes further than that, this one is higher, so it will immediately begin to pull back. And so you'll look very close, you might see some, some ring, some little movement of the signal there, but it's fairly minimal. These things will follow that signal very closely. And so in a circuit like this that we're going to use it in, it functions essentially perfectly. And so that is our little lesson on the operational amplifier, which will bring us up to speed on talking about the rest of the circuitry that we're going to describe, having to do with the architecture of a typical analog synthesizer that has storage.